Hi. All right. You're ready, right, Lawrence?
Yep.
Right. So it's a great pleasure, Lawrence Loorents from Cambridge, from DAMT, talking about matrix product operator symmetries and dualities, theory and application. Please take it away.
Okay. Thanks very much, Sakura and Sal, and the other organizers for inviting me. It's been this seminar series has been great. I'm quite amazed that you guys have kept this going for so long for a Zoom seminar. I think that's pretty impressive. Um, so today I want to talk a bit about work that we've done over the past few years. So this is not going to be a talk about one particular topic. It's more going to be an overview talk. So I won't go in depth about many of the things that I will talk about. So I just want to give like an overview of the kinds of techniques that we use and the kind of tools that we have and the kind of questions and applications that we can apply these things to. Because I think they're very complementary kind of techniques that have been developed by other people here present. And so I think it's very worthwhile, I think, to kind of compare notes and see if by combining these kind of things with tools that other people here have, we can make some progress. So the topic of this talk is MPO symmetries and dualities. And so what I want to do first is kind of emphasize that these matrix product operators, which I will explain in detail what they are, what they do is they give you the kind of the lattice representation theory of 1D generalized symmetries and by extension dualities. So I will explain in detail what that means, but the second part of the talk is then going to be about how you can actually apply these tools and techniques to actual problems in physics that we actually care about. So one of these things is the classification of duality transformations. So if I give you some theory in 1 plus 1 dimensions, what are all the possible dual theories that have the same spectrum but that realize the physics in a very different way? So there's some classification of these things that you can do using this lattice representation theory. Um, you can write these generalized symmetries and dualities if you represent it as matrix product operators. You can write them as unitary quantum circuits. So there's all the necessary technical ingredients to do that. There's a relation between these dualities and generalized gauging. So this generalized gauging is something that's been studied for these categorical symmetries for some time. And you can show that this is actually related to this notion of duality that I've discussed before. Some more recent application that we did is that you can cook up this kind of lattice analog of this famous monopole scattering puzzle in quantum field theory of Kalan. And so we have some recent results that we'll talk about where we show that there's kind of like a lattice analog of this kind of thing. And then finally, this is something that I've talked about quite a few times already. That's why I put it at the end. So I might not get there, but that's fine, or I might have to go through it quickly. But these matrix product operator symmetries, understanding their lattice representation theory really allows you to more efficiently simulate or find ground states of local gapped Hamiltonian if you're in some phase, because it explains the entanglement structures that you need to be in that phase. And if you know that, then you can exploit this in numerics. Okay. If there's any questions at any point, I think I've sort of have I won't probably won't do a full hour. So if there's questions, please feel free to interrupt me. So I have to talk a bit about MPO symmetries, and because these are a bit more general than I think most people realize, or people that have worked on categorical symmetries realize, I want to start from a very simple example that already shows you how complicated these MPO symmetries can actually get. So it's one of the oldest versions of an MPO symmetry that was discovered, but it took the longest time to really understand what was going on. So let's take the following Hamiltonian, which is basically some Pauli X term and then some cluster state type Hamiltonian. Um, this model has been studied before. It's been called the Levin Gu edge Hamiltonian. What's important to know about it for for the purpose of this talk is that it's equivalent to the XX model. So the XX model is just the XY model, which just describes a compact free boson. So this is critical theory, C equals 1. This symmetry is well known to commute with the following Z2 symmetry. Sorry, this Hamiltonian commutes with the following Z2 symmetry, which is a quantum circuit symmetry. So it's obtained by taking the cluster state entangler, which is obtained by taking a product of controlled Z gates. So that's a depth 2 quantum circuit, and then doing a local unitary transformation, which is just the poly Z times the poly X. So because the Zx is Iy, we call this the CZY symmetry. And if you square this operator, it's very easy to use whatever your favorite graphical calculus is to check that this is indeed a representation of Z2 because it squares to the identity. And so for those that don't know, this cluster state, this controlled Z gate, you can write it explicitly like this, but it's just a diagonal matrix with ones on the diagonal, except for the last row and column there, there's a -1. So this is an entangling 2-qubit gate. So this is not just an on-site symmetry, it's an entangled symmetry. And the question that we're trying to answer here is, okay, what is the algebraic structure underlying this kind of symmetry? It's a very simple symmetry, it was studied a long time ago, but it is actually a little bit complicated if you kind of just run the machinery and see what you get out of this. And so the way we will do this, the way we will analyze the symmetry is we will write it as a matrix product operator. So a matrix product operator is literally that. It is a operator that's a product of matrices. So one way to think about it is that you have this UCZY, which you can express as the sum over a trace of this product of matrices. And these matrices, they basically determine the coefficients of this operator in this computational basis, right? And so if you have an on-site operator, for instance, which is just a tensor product of local terms, then these matrices would just be 1-by-1 matrices. That would give you the on-site symmetry case. But more generally, these matrices do not have to be 1-by-1. And if they are not 1-by-1, then this operator encodes some kind of correlated action on your neighboring degrees of freedom. You might have seen matrix product states before. This is just the operator version of that. So if you want to write this operator that I talked about before explicitly, you can do this very simply with these two rank 4 tensors, which have these off-diagonal components. They have to be off-diagonal because there's an X in the definition of this operator. So it's a purely off-diagonal operator. And you can write it just using these two matrices. The explicit form of these matrices is not very important. I just want to give it for completeness. Now, if you take a look at this Hamiltonian open boundary conditions, it actually commutes with more than just this UCZY, which is a periodic translation invariant matrix product operator. You can insert an arbitrary boundary condition and this Hamiltonian will still commute with it. You can kind of see that this is obvious because if there's no term connecting the nth and the first site, then it doesn't really matter what kind of boundary condition I put there. So if I do that, if I insert a generic boundary condition, because these are 2-by-2 matrices, there are 4 possible boundary conditions that I can put there, right? So this gives me 4 operators that commute with this Hamiltonian on open boundary conditions. Okay, that's great. But now I want to check what happens to these operators if I start multiplying them together. So we already discussed that if you take the thing on periodic boundary conditions, so if you use the identity matrix as a boundary condition, then this just squares to the identity. But what if I take these other boundary conditions and I start multiplying these? So if you do this, what you end up finding is that these things form a closed algebra of dimension 8. So you take one of these operators with some boundary condition, you take another operator with some other boundary condition, you multiply these out, and you find that they form a closed algebra. I'm telling you that the algebra is 8-dimensional. This is not obvious. This is something that you have to check, but you can do it very explicitly. And so you find that if you take these two operators that I talked about before and you multiply them together, you actually get a new matrix product operator built from different tensors, different MPO tensors, where the MPO tensors now look like this. So these MPO tensors, they are now 3-by-3 matrices. You might ask, okay, if I take a bond dimension 2 MPO times a bond dimension 2 MPO, I should end up with a bond dimension 4 MPO. Yes, that's true, but it turns out that there's a similarity transformation that allows you to kill one of the rows and one of the columns. So this is equivalent to a MPO of bond dimension 3 with these two kind of matrices. So again, if you now look at this MPO with these two, built from these two matrices, there's again 4 different boundary conditions that you can put. You might think there should be 9 different boundary conditions because these are 3 by 3 blocks, but actually these are block upper triangular matrices, so only block lower triangular boundary conditions will contribute. And then there's an additional 0 row and a 0 column. So in the end, you're only left with 4 possible MPOs. And so together with the 4 MPOs that I had from before, this gives me an 8-dimensional algebra. I realize that the details of this might have been a bit too quick to follow, but the important part is that if I multiply these MPOs that I talked about with open boundary conditions, I get an 8-dimensional algebra out of this. Importantly, this algebra is independent of the system size. So you have this multiplication here, this mu here, this multiplication of this algebra. It doesn't depend on the system size. So that's what a feature is of it being a global symmetry, right? It's something that's topological. I can coarse grain or fine grain this thing, and the algebraic structure does not change. Right, that's what I just said. And so this is something that's telling you that this multiplication is not really happening in the bulk. It's rather happening purely at the level of these boundary conditions. And indeed, if you know some tensor network technology, if you have the following condition, so now this is a graphical representation of these matrix product operators. So these white blobs here, they are the tensors that I had before. They represent this operator. This block here represents the boundary condition, and I'm multiplying two of these guys, and I'm saying, okay, they form a closed algebra, and as in, this gives me some linear combination of MPOs again. If this is true independent of the system size, so if it doesn't matter how many black lines I'm acting on or in my spin chain, if it doesn't matter how long my spin chain is, I get the same kind of algebraic structure, then you can prove that this implies that there's some kind of fusion tensors that implement this multiplication locally at the level of the tensors. And then this algebraic structure is just what you get if you use this multiplication near the boundary. So this is why it's independent of the system size, because there's basically this kind of tensor X here, which acts as a zipper that you can zipper these two MPOs together with. And that's why where the independence of the system size is coming from. Okay. And so the fact that this has to be true independent of the system size also gives you that there should be a relation between the matrix product operators on one side and on two sides. There should be a notion of coarse graining or fine graining, if you like. And that's encoded by a co-multiplication. So if you look at this matrix product operator here, by definition, because of the basis I chose for this boundary condition, it will satisfy the following identity. So these boundary conditions, you can really just think of this as having open, these red indices being open here. And then if I sum over this P, this is the same as just contracting along this index P here. So this condition is completely trivial just by the choice I made for the basis of this algebra. But this gives you this co-multiplication here, which is nothing but the dual of matrix multiplication. And so the fact that this algebra is independent of the system size implies that this multiplication and co-multiplication have to be compatible with each other. And so this is what turns this algebra into a bialgebra. I should technically say a pre-bialgebra, because when I say algebra, there's usually the assumption that there's a unit, and I'm not requiring this here yet. So this gives you a pre-algebra here. And this is kind of the most general structure of a matrix product, underlying a matrix product operator symmetry in 1 plus 1v. If you give me some Hamiltonian and tell me it has a matrix product operator symmetry, I will be able to extract this pre-algebra structure, pre-bialgebra structure. So for this example that I was talking about, this pre-bialgebra turns out to be actually quite complicated. That's why I mentioned that it took quite some time for us to understand it. It turns out that this pre-bialgebra is 8-dimensional. It is semi-simple as an algebra, and it's unital, but it's not co-semi-simple or co-unital. So the dual of this algebra is not semi-simple, and it doesn't have a unit either. So as a bialgebraic structure, it is actually quite a complicated thing. And so in general,
I have
this
a
MPO,
question, Lawrence.
yes, sure.
How important is it that your MPO is translation invariant?
Oh, it doesn't matter.
It doesn't matter.
So
I see.
yeah, yeah, you could. I will. Yeah, it's actually the very next slide. So if you look at what the MPO actually is, um, the MPO is just a combination of a representation of A and a co-representation of A. And then this choice of representation, it doesn't have to be the same on every side. So you can pick something else if you like. Like a good analogy would be I could look at a spin chain where rather than just having spin one halves on every side, I could pick a spin one half on the even side and a spin one on the odd side. That's going to give me a different kind of Hilbert space. You could also imagine picking different two-dimensional representations along the chain that would give you a non-translation invariant Hamiltonian, even though you have the same kind of tensor product Hilbert space. So yeah, those are things that you can vary.
Okay, thanks.
There is a notion of, so what I will say is that there is a notion of translation invariance in the sense that I assume that this co-multiplication um, doesn't depend on space. So I'm using the same co-multiplication everywhere. This is something that you could weaken, and then you get into a whole lot of other kind of construction. So you could imagine taking a matrix product operator, and then in the middle, you conjugate it with some quantum circuit. What that would amount to is it wouldn't change the algebraic structure because you're not changing the multiplication properties of this thing. But what you are doing is you're changing the co-multiplication locally. So that is something that you can do and that is consistent. So you can make this co-multiplication site dependent if you like.
I see. So if
But
my MPO had site-dependent MPO tensors, then the co-multiplication would also be site-dependent. And
right.
would the
Yes.
pre-bialgebra structure be, would it still be a pre-bialgebra or would it be
I'm
something more
I'm I'm
general?
not quite sure. So this is getting into like this more affine Lie algebra type territory where you have some kind of structure that depend on space explicitly. So I'm not sure that this is properly considered a bialgebra. So in a bialgebra, you assume these things to be space independent. So I think this
Mm-hmm.
would already be some generalized notion, but it's clear that something like that should exist simply because you can take some MPO and conjugate it with some circuit that doesn't have to be
Hmm.
translation independent, and it wouldn't change the algebraic structure. So this it's an interesting question. It's something that we've thought about but haven't really pursued properly. But yeah.
Okay, thank you.
Right, so this MPO in general is some representation, is a combination of a representation and a co-representation of this algebra. Um, so these representation categories, mod A and mod A star, they come equipped with a tensor product via the co-multiplication and the multiplication respectively. So the co-multiplication gives you a notion of taking tensor products of modules or representations and vice versa. And in general, these are pre-monoidal categories. So there's always some monoidal structure here, but there doesn't have to be a unit. So calling them monoidal is not quite fair. People use pre-monoidal or semi-group category for this kind of thing. They're not very well studied because they don't seem to appear very, they don't seem to have appeared very much in the past. But the point is that matrix product operators provide the general lattice representation theory of these categorical symmetries. So I want to emphasize that I really started from some first principle kind of thing. I just assumed that I have some symmetry with some correlated action on neighboring degrees of freedom, and I extracted this algebraic structure from it. So this is really the most general thing that you can imagine. Now, this is not the kind of thing that we're used to getting. For instance, if you study something like SEM-TFT type models, you typically want a little bit more structure because you want, well, you're assuming that this theory is living on the boundary of some topological order. And a pre-bialgebra is not enough to give you something with topological order in the bulk. So you want some additional properties. So you have to add these things in. And so one thing that you have to add in is a unit. And so if this unit is co-multiplicative, then you have a tensor product Hilbert space. If it's only weakly co-multiplicative, then you have a non-tensor product Hilbert space. For this example that I had, I actually did have a unit and it was co-multiplicative. So that means I have a tensor product Hilbert space. The same for the unit. So you can you can add a co-unit. And if this co-unit is multiplicative, this basically means that these fusion tensors that I talked about, they are full rank. If they're not, then there's some additional projection involved. There's a notion of an inverse that you can have for these symmetries that you don't necessarily need to impose. This is what gives you an antipode. So this is kind of also what tells you that Having an inverse is what allows you to move this operator around basically freely. And then having a star structure is what makes the operation that moves it around into a unitary operation. And so this is what you need if you want to write this thing as a quantum circuit, for instance, or a sequential circuit, or whatever you like. And so all of these properties, they are what turn A into a weak Hopf algebra. And if you then look at the representation categories, then there's two representation categories. So the one that's actually describing the symmetries is the category of comodules over A, or equivalently the category of representations of A star. And there's another category that describes the algebra of symmetric operators, and this is the category of representations of A. So in the case of something like SU2, the category of comodules would just be vec SU2 basically, or vec G if you do finite symmetry. Whereas this category D, the category of modules, would just be rep G, something like that. So that's the kind of the standard case that in Comast matter that people have studied since time eternal, and then these kind of structures, they generalize these ideas. Okay, so that's kind of the algebraic structures underlying a matrix product operator symmetry. This is kind of where we are at with the math. There's some more questions here, of course, like if you now want to do this in high energy, higher dimensions, you need to start looking at two algebraic structures, and then, okay, you can start making the questions there to this fusion two category language. But if you really want to be as explicit as you can be in one dimensions, you really do need this algebraic characterization of these higher dimensional symmetries as well. Okay, so that was it for the quick theory part. Let's see how I'm doing on time. Okay, good.
I
So
have
now
a
I can
quick
move.
question on this slide. I
Yeah,
didn't fully understand the relationship between the first two bullet points and sorry, the first bullet point and the non-tensor product physical Hilbert space. Can you say a little bit more about that?
yeah. So if your algebra has a unit,
Mhm,
then you have an identity operator. And then there's an operation that tells you how to act with that identity operator on more than one side, right? So that's what the co-multiplication gives you. It tells you how do I act with my symmetry operator on one side. So let's say that I'm given the operator on one side, how do I act on two sides? And the structure that encodes that is this co-multiplication. And so if your unit is co-multiplicative, which basically means that the co-multiplication of the identity is just the identity tensor the identity, then if you
mhm,
take the matrix product operator corresponding to this, it will just be a tensor product of identity operators. But in a weak, if you have a weakly co-multiplicative unit, then this won't be true. Then there's typically some additional projection involved. And that projection is what encodes this non-tensor product Hilbert space.
mhm.
Does
I
that make sense? Or
um I mean I don't think I fully understand it, but I think the words make sense. So you're
yeah,
saying
yeah,
that
yeah.
you can always make the algebra unitable because I mean the identity operator always commutes with the Hamiltonian. Whether or not that unit has this weakly
Yes, exactly.
co-multiplicative structure
Exactly. Yeah.
somehow
Okay.
determines whether or not the Hilbert space can have a tensor product realization.
Exactly. So this is nothing
I
but
see.
saying that if you have like if you then assume the other structures as well, if you have a Hopf algebra symmetry, you can realize it on a tensor product space. If it's a weak Hopf algebra symmetry, it doesn't you
Uh-huh.
cannot realize it on a tensor product Hilbert space. I mean,
How does
okay,
this,
you
can I ask about this also? So
yep.
how does this actually tie in with these recent results about the integral and weakly integral fusion categories? Whether,
Right.
the
So
criteria, whether you can realize them on a tensor product Hilbert space with or without QCA addressing.
right. So all the things I assume here, they do not involve mixing with translation symmetry. So if all you ever do is just multiply these operators together, then this is the full story. And then, okay, then basically the statement is that what a necessary condition. So the quantum dimensions of the representation category of a Hopf algebra are always integral. So that's a necessary condition to be able to realize it on a tensor product Hilbert space. If you allow mixing with translation symmetry, there's additional operations that you can realize on a tensor product Hilbert space, like Gram-Schwann duality, for instance, has a quantum dimension square root 2. But if you
So you
mix,
don't
so
make a
by
statement
itself,
about this.
sorry?
So you don't have a general statement about when this is possible.
No. So no, indeed. So if without mixing with translation symmetry, I have, and then this is just the full story. With mixing with translation symmetry, that's what indeed these recent works are about. Then I'm
So
not
this
quite
is,
sure.
you
Well,
have no,
I think it's not known what the general thing is. Indeed,
I
yeah,
think the conjecture thing. Thanks.
yeah. No,
I have a question about
I'm actually staying. Sorry, yes.
yeah, sorry. So I have a question about the setup. So initially you're talking about MPOs. I thought they're acting on tensor product Hilbert spaces. So if your spin chain does not have a tensor product Hilbert space, what's the definition of MPO?
So my MPO is it doesn't necessarily have to live on a tensor product Hilbert space. So it is true that by writing it as an MPO, there is kind of an implicit assumption that I embed it into a tensor product Hilbert space. So my definition of tensor product Hilbert space is just looking at the identity operator. If the identity operator is not a tensor product of identities, then I don't have a tensor product Hilbert space. But any Hilbert space, no matter how entangled it is or how non-tensor product it is, you can always embed it into a tensor product Hilbert
Right.
space, right? So the point is just that when I say tensor product, I mean having an identity that is literally the identity that is a full rank operation on that Hilbert space.
Okay, I see. Thanks.
Okay, good. So that's kind of the theory part. I think this kind of nice. It took some time to fully settle and to really appreciate that already in some very simple quantum circuit symmetries that you write down for very well, very normal looking Hamiltonians, you need to kind of delve into this non-semi-simple representation theory. That was kind of surprising to us. So typically these spin chains that you get from imposing fusion category symmetries by assuming all these additional properties, this you get some nice spin chains, but most spin chains that you get are kind of a bit pathological in the sense that you get very large dimensional Hilbert spaces or weird non-tensor product Hilbert spaces. And so if you really want to capture all possible symmetries of actual realistic looking Hamiltonians, it turns out that you need to relax some or all of these notions a bit. Okay, so some applications of this kind of ideas. One is something that we did a long time ago now. And basically classification of duality transformation. So let's say that so for the rest of the talk, I will assume that I have all the properties listed on this slide. So I am in the weak Hopf algebra case, so I'm dealing now with fusion category symmetries because I can say the most in that case. Some of the things I will say generalize if you drop some of these assumptions, but we haven't really sorted out what remains and what gets killed. So I will just assume it for simplicity now.
Sorry,
So let's say
Loorents,
that I have some.
can I ask a question
Yeah,
before we move on?
yeah,
You started
sure.
with the CZX example.
Yes.
From that MPO, like if you extract all of this pre-algebra structure, is it possible to also get the 3 cocycle?
Yeah, sorry, that's a very good point. Yeah, great. So if you look at the representation category of this thing, I think I mentioned it here. No, here. Well, okay, whatever. If you look at the representation category of this algebra, you get this weird non-monoidal but unitary thing. Okay, but that's just a representation. If you look at the co-representation category, which is actually the thing that describes the symmetry, this is some non-semi-simple tensor category, but it admits a semi-simplification to twisted Vexy2, basically. And so that's how you extract the tricocycle. So you can see that there's a semi-simple category sitting inside this non-semi-simple tensor category, and that gives you the tricocycle basically. So you can actually explicitly check the associativity of this local fusion process here. So the thing that I have on the bottom left here. If you check the associativity of this thing, you get a minus sign, and that's signaling that you have indeed this tricocycle. If you do the same thing for just the CZ, which is a non-anomalous representation, non-anomalous, non-on-site representation of Z2, you don't get a tricocycle. So this algebraic framework really recovers these anomalies correctly. Yeah.
I see. So in the CZ case, you just get a semi-simple thing on the nose. Is that right?
No. It's still non-semi-simple, but the semi-simplification is just normal Vexy2.
Okay. I see.
So already for just the simple cluster state entanglers, you need these weird non-semi-simple categories. So it's a bit unfortunate that the situation is like this, but it is literally just that is the structure that you get. We did not get to pick this.
Thank you.
Okay, applications. So Let's assume that I have some fusion category symmetric nearest neighbor Hamiltonian. It doesn't have to be nearest neighbor Hamiltonian. Could be a transfer matrix of some stop-Mackball as well. It doesn't really matter. It's just simplest to explain it like this. So let's say that I have a Hamiltonian that's a sum of local terms like this, and it commutes with some matrix product operators with some boundary condition B. So it follows then from Schur's lemma that this Hamiltonian has to be composed from intertwiners of that symmetry. So this is kind of saying that, let's say that you have some SU2 symmetric Hamiltonian. It's saying that any Hamiltonian that commutes with the SU2 symmetry has to be composed from the Clebsch-Gordon coefficients of that symmetry. And the kind of nice thing is that this is still true for these matrix product operator symmetries. So there is a Schur's lemma, or there is kind of basically a Wigner-Eckert theorem for these generalized symmetries. So there is really, you can mathematically prove that if an operator commutes with this MPO symmetry, it has to be built from intertwiners of that symmetry. And this is kind of a rigorous formulation of this topological holography or SymTFT idea that you basically have a layer that's responsible just for the symmetries, which is this layer of Clebsch-Gordon coefficients. And indeed, these Clebsch-Gordon coefficients, they are what build up your topological field theory in 2+1 dimensions. The Tura-Viro state sum gives you those intertwiners. And then there's some layer that's just encoding what representations do they pick. So this is kind of like the physical boundary in the SymTFT picture. This works in the fusion category case, but it's clear that this also works for SU2 symmetric theories, for instance. Applying this SymTFT idea to SU2 symmetric theories is a bit of a stretch because there's not really or at least it's a bit more subtle to define a TFT based on an SU2 symmetric theory. Or if we go back even further to the beginning of the talk, if you want to define this Hamiltonian based on this with this cluster state entangular symmetry, the CZX symmetry, then you would need to cook up some non-semi-simple topological order, and these kind of things get a bit complicated. So this kind of theorem is telling you that indeed that is possible. So okay. So what you can do now is if you have kind of all possible symmetric operators like this, you can look at the algebra generated by these local symmetric operators. This is called the Bond algebra. It has different names in various contexts. In integrability, people have studied things like Templey-Lieb algebras extensively. So these kind of things have popped up many, many times before. We just used the name Bond algebra because it was convenient. And if you look at sort of the taking products of these local operators, you find that the structure constants of this algebra, so you go to some basis for this algebra, and then you start multiplying these things, and you can always bring it back to some standard basis. The only thing that you have to do to bring it to the standard basis is basically use the associators of the representation category of this symmetry. And so you have to only use the F symbols or associators of this fusion category D. And so what this is saying is that if you can find different models with different symmetry, but the same Bond algebra, they will have the same spectrum, basically, up to degeneracies. And so the way to do that, which what we showed in this paper some time ago, is that the different ways in which you can do this, the different ways in which you can write down intertwiners that are recoupled by the same associators, they are actually classified by a module category over D. So different choices of module category will give you dual models that have the same spectrum. And so the reason for this, one way to understand this, is that there's a one-to-one correspondence between weak Hopf algebras and invertible CD bimodule categories. So if I give you some weak Hopf algebra A, from that you can extract this invertible CD bimodule category. Then the question is, okay, if I do a duality, this now amounts to keeping D fixed, but changing this R, or equivalently changing A to some A prime, such that this category D is still the same. So this category of that describes the algebra of symmetric operators is still the same, but everything else changes. So the symmetry can look very, very different. So you can go from a VecG to a RepG symmetry, things like that. And so this changes the Hamiltonian and the symmetry, but it's an isomorphism of the algebra of local symmetric operators. Okay, so the second application you get from this, oh, yes, there's a question.
Yeah, thanks. On that previous slide, so
Yep.
this is kind of like an atomic duality, but one model to one model, right?
Right.
So, but in general, of course, you can get, duality groups, families of dual theories.
Right.
How does that manifest itself in this description?
So I mean, there's different. So given this representation category D, there are typically many distinct choices of realizations of this category of symmetric operators, and all those models will be dual to each other. So for instance, if I give you a model with an S3 symmetry, there will be four different realizations, and all those four are dual to each other, and you can start composing dualities, and okay, they will form non-trivial groups. So sometimes you get a duality, sometimes you get a triality, but it's
Yeah.
all the same kind of structure. So this just gives you
Yeah,
all the dual models, and then the maps between them you can compose, and they will give you
I think
different
it's
kind of
useful because
structures.
Dan is a high energy physicist, I think by training, if I'm not mistaken. That when you talk about duality, we should really think about gauging.
Yeah. So this is
So
the
this is just
next,
literally
well, this is
gauging the
application
symmetry from
3.
S3 to rep S3 to rep S3 mod Z2, etc.
Exactly.
So
Yeah,
it's
yeah,
not
yeah.
too confusing.
So in that sense, I know there's sort of a tension, and I will hopefully resolve this tension with my application 3. But
Yeah.
indeed, when we say duality in condensed matter, historically it has meant really like an equivalence between two theories, where really the full UV theory matches the full UV theory of another. So it's a full spectral equality, and any correlation function in one theory can be written as a correlation function in another theory, but the locality of the locality of these correlation functions might change and things like that.
I
So
think
in
I
that
mean I
sense,
think I mean exactly the same thing when we talk about duality. I think we can agree on that.
okay, yeah, it's been a bit hit and miss talking to high energy physicists. So some of them will happily agree, some of them will disagree. So
Okay.
I think I can make very precise that these things are equivalent to gauging. So in
Perfect.
that sense,
Okay.
and I think that's a bit less ambiguous, but I will get to it
Thank
in
you.
a bit. Thanks.
Why do you imply that the set of duality transformations form a group?
So in some cases they do, right? If I look at the
Well, in some
category
cases,
of
I have no
all,
problem, but
no. So
because
of course in
sometimes you
general,
cannot compose all of them. So
you're
if
right.
at
You're
all, they
completely
form a
right. So in
semigroup.
general, I would have to call it a groupoid. So I was thinking of the case where if I
Okay,
look at
groupoid
the
is fine.
category of all
Fine.
CC invertible bimodal categories, it's this Brouwer-Picard group. But indeed, in the more general case, it's a groupoid. So of course, yes, you're completely right. Thanks. Okay.
Actually, since I interrupted you, and I'm perhaps one of the few high energy physicists here, and since I'm also partly responsible for the terminology, I wanted
Yeah,
to clarify what you said earlier about high energy physics.
sure.
It's often called duality when the two different theories are completely equivalent.
Yeah.
And the other notion is referred to as infrared duality, where they are the same only at long distances.
Yeah, indeed.
And with these two definitions, I'm completely in agreement with you.
Okay, great.
So, but there's a different term for that, which is infrared duality.
I see. Okay. Yeah, no, that makes a lot of sense. Thanks very much. Okay. So application 3, if you keep track of the boundary conditions, basically, then these dualities are actually isometries. So you can relate the full spectrum of one theory to the full spectrum of the dual theory, but you have to keep track of the boundary conditions. So in that sense, these things, they are invertible. And this, like Kramer-Johanny is an invertible transformation, but you have to allow it to act on the boundary condition. You have to allow it to change from an untwisted sector to a twisted sector. And if you include all those sectors at the same time, then you actually get a unitary equivalence in the case of Kramer-Johanny. And so what it means is that at the level of these matrix product operators or these individual tensors that realize these symmetries, you can really explicitly see this because these tensors, you can write them as unitary quantum gates. So this matrix product operator tensor here, in the case that I have a unitary fusion category symmetry that describes it, it is actually a unitary quantum gate. The same goes for these fusion tensors. They are actually unitary transformations. These Clebsch-Gordan coefficients, they are actually unitary transformations. And so if you have that, then you can actually write these generalized symmetries as quantum circuits. So what you do is you add some ancilla So let's say that I'm on closed boundary conditions here. I add some ancilla here, and I can move this duality operator all the way to the left, and then I can merge it with what I already had. So let's assume that I already have some twisted sector here. I have to fuse with those two. I get something else, and then I have to fuse again. But all of these are completely unitary transformations. So from this point of view, it's kind of clear that these things are unitary transformations, but you have to introduce an ancilla here. And this ancilla actually gets mapped to the different charge sectors. So there is a basis in which you can measure these gray additional degrees of freedom that you didn't have in your original system. And there is a basis in which you can measure it where this basis just corresponds to the different charge sectors and the different boundary conditions. So this is a general thing. You can always write down this generalized symmetry operator or these dualities as a linear depth circuit. And that makes sense that it has to be linear depth, because it has to be able to take a local operator to a string order operator. And that's something that you can only do if you have a linear depth circuit. It couldn't be a constant depth circuit, for instance. So that's compatible. However, if you allow yourself to do measurements, which is something that you can also do, then actually many of these operators you can write down in constant depth. So you get this absolute beast of an expression here. I'm not going to explain it in detail, but it basically boils down to the fact that you can, rather than just inserting these ancillas on one side, you can do this everywhere and then fuse things together. You will get some errors. But in the case that you have a nilpotent duality, which is the case where your dual symmetry is actually given by a nilpotent fusion category, in that case, you can actually correct for these errors in some constant depth way. And so in this way, you can actually implement these duality operators in constant depth if you have measurement. And these kinds of ideas and similar ideas have been used to prepare quantum states on quantum computers, because these dualities, they map between non-trivial phases. So I can prepare a state in some SPT phase by acting on a product state with this constant depth quantum circuit. And actually the 2+1D version of this also somewhat works. This is what has been used to create non-abelian topological order on quantum computers. So these kind of tools and techniques, they are actually used in practice.
Loorents, what does it mean for a fusion category to be a nilpotent fusion category?
So nilpotent means that it's graded all the way down to the identity. So you have a fusion category, it has some grading. If you look at the identity component of that thing, you get another fusion category that might be graded again. You look at the identity component of that, you get another fusion category that might be graded again. And if you keep doing this and you end up with the identity category, so just the category vec basically with one object, then it's nilpotent. So an example would be Ising. Ising is nilpotent. It has nilpotency length 2, because if you take Ising, it's C2 graded. You look at the trivial component, you just get vec C2. You look at the trivial component of that, and you get nothing, right? You get the identity.
Yeah.
So that means that's what nilpotent means. This nilpotency property, the fact that it's basically a series of potentially non-abelian group extensions of the trivial category, is what allows you to clean up these errors in constant depth, basically.
I see.
So
Did you say that if the fusion category symmetry is dual symmetry is described by a nilpotent fusion category, then the original fusion category symmetry can be written like on the right?
The statement is that if you do a duality and the dual symmetry is nilpotent, then you will be able to implement the duality in constant depth with measurement. Because the errors are given by the dual. Basically, you get some twisted sectors in the dual, and you have to clean those up. So it's those that have to be nilpotent. Yeah.
Okay, I see. Thanks.
That's not the full picture. So for instance, something that is not nilpotent is rep S3 because it's not graded. But there's actually other tricks that you can do to still do that one in constant depth. So we haven't fully explored this. This is not if and only if. The statement is that if it is nilpotent, you can do it in constant depth, but it's not because it is not nilpotent and you cannot do it in constant depth. There are other tricks, but we couldn't really find like a unifying feature of these things. So we just left it at this.
So Fibonacci, presumably you can clean up in this way.
Yeah, I doubt there's any hope for Fibonacci. This is just has almost zero structure. I mean, it's a
So it
cyclical
has to
fusion
do
category.
in the rep S3 case with the fact that it's essentially group theoretical.
I'm not sure. Yeah, I
I
don't
mean, you
want to
could
make a
go into
definite.
right, because the in the case of the group symmetry,
Yeah.
if those are the charges, maybe you
Yes.
could use some finite constant depth circuit.
Indeed. Yeah, I mean, there should be some invariance under Morita equivalence here. Like the fact that you can do it for VecG, but not RepG. Like RepG is not nilpotent, but VecG, of course, is. But it seems that this notion of being able to do it in constant depth should be stable under Morita equivalence. And indeed, the kind of way you do it for RepS3 is you do a combination of Kramers-Wanier for the Z2 and the Kramers-Wanier for the Z3, and together they kind of combine in a nice way to be able to do it. And that's also how people did it in higher dimensions. So I'm not sure. I think it's worth to explore this a little bit further. But yeah, I don't want to make a definite statement. Okay. Yeah, so application 3, dualities and generalized gazing. So here I hope to sort of clarify a little bit, but as far as I understood, I think we are all in agreement here. If I give you some categorical symmetry, you can gauge this. You can gauge a symmetric Frobenius algebra inside this fusion category symmetry by basically inserting in your partition function a network labeled by the algebra and then using your multiplication and co-multiplication to define this sort of defect network and sort of summing over all these configurations. On the lattice, for a quantum Hamiltonian, this is given by something called the gauging map. So now I'm using a slightly different calculus. You can sort of ignore these blue lines if you want. So this is literally just this gauging map is obtained by taking your Gauss constraint, which is also constructed from this algebra object, and then constructing a projector onto the gauge invariant subspace, taking the product of all of those guys and acting on the trivial gauge field configuration. So that's the gauging map. And this is something that from a original state in your pure matter theory will construct you a state in the gauge theory with gauge fields, but in the gauge invariant subspace. So this is basically a way to generate states in the gauge invariant subspace. I should also emphasize that this is flat gauging, right? This is not there's no curvature for the gauge field here. And so there's a trick that you can do to show that this is actually completely equivalent to these dualities that I was talking about. So there's something called the internal home, which if you have a module category of some symmetry category C, then there's this object that you can construct inside the original category. That's actually an algebra object, and it's basically obtained by taking this module object and multiplying it with its dual. So if you do that, you will get an algebra object. So in that sense, you can kind of think of these module objects as the square roots of this algebra object. But now these module objects, they are exactly what label your duality operators. So if you compare these two pictures, the only thing I did really was just use this isomorphism. So I took this algebra object and I took the square root of it. So I pulled it apart into x and x bar. That's what gives me this picture. So what I get is this operator labeled by x on the bottom here. This is exactly the duality operator. And then on the top here, I get some stuff that I can remove in finite depth as well. So this is just some local unitary transformations that I'm doing here to show that this gauging map operator is completely equivalent to this duality operator. So when I'm using this notion of duality as being a map from one module category to another module category, they are really completely equivalent to this notion of categorical gauging. So that's kind of the thing that I wanted to emphasize here.
I failed
so
to understand that. So can we take a simple example of one
Yeah.
degree of freedom in quantum mechanics? And in this case, duality transformations are the same as canonical transformations.
I'm not quite, yeah, I'm not
In what sense is it the same as gauging?
Well, if you just have quantum mechanics and just 1 degree of freedom, I of course don't have all this additional structure, right? I just have.
Well, it should only get better, not worse.
Yeah, I have thought about this. I'm still not quite sure how to properly decategorify this idea, right? So this is.
But more generally, like the theory and the gauge theory are not dual to each other.
Right. So this is flat gauging, right, of a finite group symmetry. So
Even with finite groups,
right.
In general, they're not equivalent to each other.
But would you be happy to say that for that Kramers-Wanier can be thought of as the gauging of a Z2 symmetry?
No.
Okay, yes. And then I think there's some
You and I
terminology.
discussed that at length.
I know. So what I mean
And I
here is
maintain
that,
that duality and gauging are not the same thing.
right. I think it has to do with what you allow the dual theory to have in terms of boundary conditions, right? So
Okay, let's put it on compact space, so I don't need to discuss the boundary conditions.
okay,
Duality is not the same as gauging.
right.
Okay.
Yeah, I know we've discussed it before, and I doubt that we're gonna sort this out in this meeting here. But what I can show is that these operators that I use that implement my Kramers-Wanier duality on my spin chain are unitarily equivalent to these gauging maps that people use to gauge these operators. Now, there's a question indeed of what you do if you have boundary conditions and what happens to your twisted boundary conditions. And I think the subtlety lies there in how we choose to identify this with the dual theory, or what do we allow the dual theory to be? Is the dual theory still just the thing of periodic boundary conditions, or do we allow it to have anti-periodic boundary conditions as well? Do we think about the boundary condition as being a dynamical degree of freedom, or do we think about it as some kind of different sector that I shouldn't be considering both at the same time? I think that's where the subtlety lies. But there is okay. I guess I want to say that there is at least some part of the math that shows that these two things are the same, and I think it's an interpretation whether or not we actually say that these are completely equivalent or not. Okay, but let me move on to another example. So something that we did more recently was this sort of lattice version of this monopole scattering paradox. So this sounds very complicated, but it's actually, depending on how much you know about these lattice symmetries, this is almost completely trivial. So there's this famous monopole paradox that Kalan posed in the 80s, where you take a wild fermion, you throw it at a magnetic monopole, and what you get out as a scattering state is this fractionally charged wild fermion. And so for a while, this puzzled people, because this shouldn't exist. This kind of thing is not physical. You shouldn't have fractional charges. And so recently, people resolved this by realizing that actually the solution to this is that these scattered particles, they just live in a twisted sector of the original theory. So the model they have for this is that you kind of take this picture B here, you take this fermion, you throw it at the monopole, you get some outgoing state, but this outgoing state is actually living in a twisted sector. So if you think about this from some lattice point of view, you have a Hamiltonian on the left, you have a Hamiltonian on the right, and then you have some impurity Hamiltonian that couples to this impurity. You throw a fermion or a particle at this impurity, and the particle that comes out on the other side has some string attached to this impurity. And so this way, well, these people there were kind of able to resolve this monopole scattering paradox. And the question is that we had, which is kind of an obvious question, is how generic is this? Can you realize this kind of thing in a lattice model as well? And so what's kind of clear from the fact that these dualities, they are topological
Sorry,
operators,
can I
and they
just
can
ask, so,
yeah,
I mean, the monopole scattering is something in 4 dimensions.
sure.
And I think you probably, I think these results are, the thing with the precise results are really a 1 plus 1D analysis, right? And you're gonna do a lattice
Sure,
model in 1
Yeah,
plus 1D.
sorry. So this is
I
like
I think
a one.
I don't think you'll be doing this in the 4 higher dimensional theory.
No. Well, not yet, at least. I mean, we did a 1 plus 1 and a 2 plus 1D thing. But indeed, the precise analysis is using boundary conformal field theory in 1 plus 1 dimensions, exactly. Yeah. Still, the features, I think there's well, an analysis of the 3 plus 1D case as well, and I think it's expected that this is kind of the same. So this paradox already exists in 1 plus 1, and I'm focusing on that case now. But indeed, the original one is a 3 plus 1D, of course. So if you have these dualities, and because I mentioned they give you a full spectral equivalence between these two theories, if you take one theory on the left side and another theory on the right-hand side, and they're separated by this duality transformation, because you can move this duality transformation with a local or unitary transformation, what you will find is that if you take a wave packet, so a localized particle, and you shoot it through this duality defect to the theory on the other side, it will perfectly transmit because the energy levels, they match, right? So there's no like reflection going on. But this scattered state, it could live in a twisted sector. And so one of the examples that we did, but we did many examples in this paper, is you just take the Ising model, right? So you take the Ising model on the left, you take the dual version of the Ising model on the right, and then this duality defect between them enforces some very particular interaction with the impurity degree of freedom, which is this. And if you do this simulation, so you really make a local wave packet, which is something that covers basically the entire spectrum, right? So it's localized in space. It's localized in real space, which means that in momentum space it's completely non-local thing. So it really covers the full spectrum of this Hamiltonian. You take this particle, you make a wave packet out of it, so you make a kind of Gaussian wave packet. You make this propagate to the right-hand side. And this is kind of technical, it's a non-trivial numerical simulation to do this. And you shoot it through this duality defect, which is marked in gray here. You find that it goes through completely, right? So there's no scattering going on. It doesn't bounce back at all. But what happens is that it becomes a domain wall excitation, basically. So it drags a string behind it. And so this scattered particle lives in a twisted sector of the original theory. And so this is kind of a lattice analogon of this monopole scattering idea. And using this representation theory that we have of these matrix product operators, there's many, many examples that you can do this with. I think we also did a 2+1D example in the paper, but it's kind of hard. I would have to show you an animation, and including an animation in a PDF is much harder than any of this. So I didn't bother. Okay. I think with that, I am almost out of time. So, which is kind of what I was planning for anyway, because the last thing is something that I've talked about quite a few times already. It's how understanding these matrix product operator symmetries in detail and understanding their gauging or dualizing and being able to map between different phases allows you to do better numerics. So since this is something that I've talked about quite a few times, let me just skip this and go to kind of the punchline. So there's this idea that, let me see here. The main result is here, I think. Yep. So the point is that if you want to simulate, if you want to numerically obtain the ground state of a Hamiltonian in some phase, because it is in that phase, there will be some entanglement in that ground state. Like if you have an SPT phase, for instance, there is some entanglement in that ground state that is there just because it has to be in an SPT phase. And the point of these dualities is that what you can do is you can always map to a theory where the symmetry is completely broken. So a dual theory where all the description is completely equivalent. Any correlation function in one theory I can compute in the dual theory. But because the symmetry is now completely broken, there's not this entanglement cost associated to being in a phase. And so the kind of result that we have is that if you have a Hamiltonian with some categorical symmetry C in some phase P, there's always a dual Hamiltonian with a dual ground state that completely breaks the symmetry. And this dual ground state has no redundant Schmidt value, so that the entanglement degrees of freedom are all independent. This minimizes the entanglement and the bond dimension that you need to represent the state. And also because the symmetry is not there anymore, all your variational parameters of your ansatz are truly independent. And so your computer can use its full memory to actually explore distinct states. There's no redundancy anymore. And so if you combine all these things together, you end up with this kind of nice picture where you have these various fusion categories and module categories and bimodule categories. And you get this kind of nice picture of these categorical structures in 1D phases of matter. So there's something that describes the algebra of symmetric operators. There's something that describes the symmetry. These are connected by this representation category R that I talked about here. And then there's the phase, the quasi-particles, the entanglement, and there's a very nice combination of all these kind of things that you can really explicitly work out, and it gives you faster numerical methods to obtain these ground states. So that's kind of the last thing I wanted to mention. And with that, I thank you for your attention.
Okay, thanks a lot for the talk. Are there any other questions? I had lots of questions and discussions, also in the chat that you might not have followed, but I think there's agreement among some of us that we should not call these things dualities, but I don't think we'll resolve this entirely in this finite amount of space.
Oh, I see.
And time in particular. Are there any other questions? So how much of this can actually concretely be done in 2+1D, where, indeed you might want to, model some fusion 2 category symmetry, or, not just something that's 2-vec G, but something that also has some Brady diffusion category stacked on top, where you have a generalized gauging. Right. So how much of this can be actually equally efficiently implemented?
It depends a bit on how. So the problem with fusion 2 categories is not so much the formal definition of these things. I think there's some consensus on how these things should be formulated now.
I think they're classified now. Bosonic ones, they're fully classified.
Right.
By T-Bourne inference.
But so the problem with these things is that it's much harder to be as explicit in computations, because computing the data of these fusion 2 categories is just much more complicated, right? Already, it's very akin to computing the associators for a non-semi-simple fusion category. So defining F symbols when you have non-trivial endomorphisms of your objects. If your endomorphism algebra of an object is non-trivial, you have to mod out by these things when you're defining F symbols. And it's a very similar situation that you get in 2+1 dimensions, because some of the data of this pentagonator, which is basically the defining piece of data for these things, well, you have these certain things are labeled by fusion categories, but then there's things that, well, functors basically, or module categories, and there's functors between these module categories, and you have to mod out by these relations. So defining this skeletal data, basically, that I'm saying, defining the skeletal data of a fusion 2 category in the completely general case is kind of complicated. We can do it for 2-vec-G.
One advantage is that all of these are, group theoretical. One complication about fusion categories in 1+1D is they're not group theoretical. Tampere origami, some other stuff. But here you argue with whatever.
So when you say
in 2+1D, it's really everything is gauge related, generalized gauge related to 2-vec-G May with an anomaly. So that should give you, since you keep talking about gauging, there should be sort of a way of now constructing and determining all the structure. Because for the 2-vec-Gs, the associators are, all of that is pretty clearly known.
Right. So what I'm saying is that, I mean, it's not because it's gauge related that it's some simple thing, right? What I mean is that
complicated, but I'm saying,
we cannot mod out by this notion of equivalence.
We could write down lattice models for these things with Kansai collaborators, right? So it's like, it's extremely concrete, and because it's group theoretical, it's quite general.
Right. So
just wondering, why now there's not. You seem hesitant. I'm just trying to see what exactly is the obstruction.
No. So I completely agree that for things like 2-rep-G, 2-vec-G, these kind of things,
even for things that are with attachment of a Brady diffusion category that you stack on top before you gauge. For the general thing.
Okay. Then I would say then I would expect most of these things to go through. Of course, there's differences in having, well, higher form symmetries, in the sense that, for instance, this idea of being able to move the 2+1D Kramers-Wanier duality, right? On the gauge symmetry side, you get these closed loop constraints, so you cannot quite move it freely, right? If you move it somewhere and then you move it back, you will get this it's not going to be a unitary transformation. It will be an isometry because you will get this projection onto this closed loop constraints. So things like that are more subtle because you have a higher force symmetry. The
You mean
kind
like
of
Gauss law
main,
constraints?
sorry?
You mean like Gauss
Yes.
law constraints?
Well, not really Gauss law constraints, right? The dual, so the non-topological one-form symmetries. So just the
Yes.
symmetries you get on closed loops. I wouldn't call these Gauss law constraints, but
Okay.
if your duality operator or your gauging map or
You
whatever
can,
you want to call
yes.
it, only has support on the subspace where these closed loop symmetries are satisfied, right? Because only on that subspace
Okay.
is there equivalence between these two. So if you take something like your 2+1 Kramers-Wanier, you move it somewhere and then you move it back, you're not left with nothing, right? It will leave behind the projection onto this kind of thing. So those are subtleties, and they are actually, I mean, they sound maybe not so bad, but for instance, this idea of mapping to a dual theory where you completely break the symmetry in 2+1 dimensions, this is much more complicated because the dual symmetry that you're breaking is a one-form symmetry, and it's not at all clear that breaking
You
of a
get
one-form
topological
symmetry.
order.
Exactly. It's not clear that that's easier to simulate numerically, that there's less entanglement associated to this than there is to a zero-form symmetric phase, for instance. So
Sure.
there are
But the
subtleties
good
there.
news is you can always map it back to something that's group theoretical. So, yeah.
Right. Yeah. But the whole point is that, I mean, we typically, the kind of idea is that we gauge the symmetry. You gauge the unbroken symmetry basically to go to a completely symmetry breaking phase. And if you do that in higher dimensions, you will map to one form symmetry breaking phases. And there's subtleties with these.
Yes, I mean, but it is, that's part of the interesting thing in high dimensions, that it's not just SSBs and numbers of vacuum, but it's actually actual topological order. And one would like to efficiently simulate that. Anyway, so
Right.
there's been lots of discussions also in the chat about this terminology.
Yeah, I'm just having a quick
I think
read through here.
some of us agree it shouldn't be called a duality, but I think what Andrea suggests to call it a gauge-related model, or maybe a Morita equivalence, right? That's sort of what mathematicians call it. Okay, I don't think there are any other questions, so I will stop the recording. If you can also stop the recording.